Centuries before digital networks existed, European monarchs, diplomats, and spies transmitted their most sensitive data across physical space. A sealed pouch carried by a single courier through the forests of Europe was highly vulnerable to interception. Securing these communications required meeting three strict criteria. The message needed to remain entirely unreadable to unauthorized parties, its existence needed to be easy to deny during a search, and the receiver needed a way to verify that the contents hadn't been altered. While we currently rely on mathematical algorithms to protect data, early intelligence networks solved these problems by engineering the physical matter of the message itself. They used sympathetic ink. For high-stakes state secrets, the most reliable method was the iron-gallate reaction, a process that stored information in a latent state until a specific chemical trigger revealed it. This system functioned by separating the writing process into two distinct chemical stages. It essentially turned a blank sheet of paper into a medium for stored, unreadable data. This historical chemical reaction reveals a sophisticated approach to security that mirrors the logic of modern encryption, but executed entirely through molecular interaction. This photograph shows the physical tools of historical communication: an inkwell, a quill, and blank parchment. The act of drafting a secure document began with a chemical deception. The sender prepared a dilute solution of iron 2 sulfate, historically known as green vitriol. When dissolved in water, this crystalline salt produces a nearly colorless liquid. A quill dipped in the solution deposits the liquid onto the page. Once the water evaporates, any faint discoloration blends into the natural texture of the parchment, leaving no visible residue. This animation illustrates the paper's microscopic cellulose matrix. Scattered throughout the gaps is the active agent, the Fe2+ ion. This reducing agent is chemically primed, ready to release an electron to the right partner. Until then, it sits dormant. In this dried state, the paper appears blank, yet it holds a precise map of information. The data is physically present in the fibers, but it lacks the visual signal required for a human eye to detect it. By removing the visual signal, the sender ensures that an interceptor cannot simply read the page. They must possess the specific knowledge required to trigger the chemical release of the information. To read the message, the receiver needed a highly specific developer fluid sourced from oak galls. Oak galls are abnormal growths that form when gall wasps lay eggs inside the tissue of an oak leaf bud. The tree responds defensively by flooding the area with complex organic compounds, heavily concentrated with gallatanic acid. This diagram displays the structural formula of a gallatanic acid molecule. The critical features are the gall groups, specifically these adjacent hydroxyl clusters on the aromatic rings. They form a bidentate ligand, oxygen atom pairs functioning as molecular pincers, perfectly shaped to capture metal ions. Crushing the galls and steeping them in water produces a clear solution. On its own, this tannic acid produces no visible mark on blank paper. This specific molecular arrangement acts as the trigger for the dormant information. The interaction is based on geometric matching. Unless the developer solution contains molecules with the exact spatial arrangement needed to bond with the iron, the underlying data remains invisible. The chemical reveal begins when the receiver carefully washes the clear tannic acid solution over the surface of the seemingly blank parchment. In the first step of the reaction, the oxygen pincers of the tannic acid encounter and immediately capture the dormant Fe2+ ions. They form a coordinate covalent bond, where both shared electrons flow in one direction, from the oxygen atoms to secure the iron. The pale iron tannate complex is highly unstable, triggering aerial oxidation. Ambient O2 collides with the complex, stripping an electron from the iron to convert Fe2+ into Fe3+. This loss dramatically alters the structure, creating a massive, delocalized system of conjugated bonds across the molecule. This vast network of conjugated bonds shifts the molecule's light absorption into the visible spectrum. The compound instantly turns an intense blue-black. Because this new iron 3 gallate complex is highly insoluble, it precipitates directly into the paper's matrix. It chemically etches itself into the cellulose, making the visible message permanent. This two-step chemical cascade functions as a precise set of instructions that the paper executes to produce a visible output. Historical interceptors understood that invisible inks existed. They routinely subjected captured letter to heat, iodine vapor, and various generic chemical washes in attempts to force hidden writing to reveal itself. These attacks routinely failed against iron gallate. Generic reagents lack the precise pincer-like geometry required to capture the dormant iron, meaning they bounce off without triggering the necessary color change. The high degree of chemical specificity meant that only a very narrow range of substances could induce the necessary change, providing a high level of security against casual discovery. To compound this security, intelligence officials embedded the invisible message directly alongside mundane information. This document shows visible cursive writing detailing ordinary business, but an entirely separate set of instructions is hidden here, in the blank margins of the page, written in sympathetic ink. This is steganography, the practice of hiding the very existence of a secret communication. By combining chemical specificity with psychological misdirection, communicators created an incredibly resilient security system. This robust chemistry was trusted by the era's most sophisticated intelligence networks. It protected troop movements for George Washington's Culper ring and secured the diplomatic correspondence of European royal courts. When the developer fluid washed over the page, the physical parchment functioned as a storage medium, releasing its contents only to the intended recipient. The system satisfied the three criteria of secure communication. It maintained confidentiality through chemical specificity, it offered deniability via its colorless resting state, and it guaranteed the integrity of the message through a permanent chemical bond. The human requirement to protect data is a universal constant. It is not strictly a product of the digital age. Centuries before information was secured by sequences of ones and zeros, the world's most vital intelligence relied on a chemical binary, colorless and dormant, or oxidized, bonded, and undeniably legible.